So also for I will study the rheological characteristic of the formulation and study rheology at basically the crossover point. And finally, I will identify the optimum point or result related to the for the viscosity and the color. So basically, the key factors cause the rejection of the lot. How? When we are performing, if the formulation of the material before running a lot patches, we try, to prepare a small model or formula from the material, like, pigment and additives, and for sure the resin. When we formulate it and run it in the extruder, then if we get the color from first time, then we are lucky. Otherwise, we should repeat it. And this is basically what happens over the world. They are losing millions of tons over the world, because they get the wastage, because they are not getting the color from first time. So the minute, weight of these pigment and additives is very significant. And also the poor process condition, like, you are dealing with hundreds of parameters or variables, like processing parameter, temperature, speed or the screw, the feed rate, any variation of the processing parameter, or you are changing the screw design of this extruder, you will get the color mismatch, which it caused a huge wastage. Also, after running the material, then we should carry in the lab. We should take consideration for the pigment size, the distribution, the blending, and maybe we'll take also sample to get the viscosity, agglomeration, and finally, this is all of these running in order to reach to the proper dispersion of the color. What is the possible reason for color mismatch? The more important is incorrect formulation. As I said, the minute preparing of the formulation is so very important. You are measuring, for example, the pigment or the additives in milligrams. So any changing, it will affect the color. Color, it is not easy thing. You are dealing with millions of color with different codes. So the second possible reason is the interaction between the material and the processing parameter. The parameter which I concentrated in my work is the temperature, the feed rate, and the screw or the speed of the screw. Poor pigment dispersion in a plastic, when you are blending the material or extrude it with different screw design, it also affects the color mismatch. So let's first, for somebody not familiar with the color, the color, how we measure the color. We, in the color space, we have we get like a figure or a number, this number gives you indication, which is called DE. DE, what is DE? DE, if you look to this coordination in the color space, for example, if you go to the right, you get A plus, it's very red. If you go to the left, then you go gray, then greenish. Same here, bluish to the right, then you go bluish. Same here, when you start going to the high, you get lightness like 100 and 0 is black. This is, so basically the values indicate for here L from 0 is delta L, and here delta A, and here delta B, which it is values indicate how much standard and sample differ from one another in color space along the coordination axis LAB. So basically we have Pythagorean theory can calculate the difference between the standard color and the real color. So basically the color is a three factor or a three matter, which it is the light, like sunlight, object, like the plastic, observer, like your eyes, which it see the color. Also, this is another diagram showing to you how the light is hitting the object, and some of the light go to different deeps, it can hit the pigment. This is the small pieces is the pigment. It gets, some of the light absorbed, some transmitted go outside, some of the light get reflection or refraction, and the one which is diffused or reflected, you will see it hit your eyes and you see the color. So basically the incident light is reflected by pigment, different colors, different depths. Then you will see finally the desired color which it is reflected. So also I talk here in this slide for the compounding material. You know, basically we are mixing two polycarbonate, Lexan polycarbonate, you know, with different multi-flow index. The first one is 25 gram per 10 minutes, and the second one 6.5 per 10 minute polycarbonate resin. The blending ratio of these two polycarbonate is like 30 to 70%. The first one 30%, second one 70%. Blended with 4 pigment as shown here: white, black, red, yellow, with different weight here. Then the percentage of the pigment or the color to the resin is 100%. The color or the pigment, it is like less 1%. It is 0.86 ratio blended. And all these material, it should be blended with a super floater. After they are blended, we will get another design, the composition. I did it. I will show it to you with the next slide. The characterization, or after we are blending this material, then all the palette, we will mold it again in a molder to get the color shapes with this dimension 3 2-point-inch, 3 different sample or shapes. With each, we will get the 3 spot in order to get, you know, a statistic, a high number of reading to calculate it and to justify our color from the samples. And from this sample, we will get sections, thin section. We brise it, or we have a micrometer sectional. We can cut it with a machine to run viscosity, rheometer running to check viscosity, or for morphological by scanning electron microscopy reading. So this sketch, I did it actually just to show it to you, all the whole schematic diagram of plastic processing method. As I show it here, we are melting the two resin with the additives, pigment, then we put it in the Coborian extruder, then it's blended. After that, we will get the belterizer, and the belterizer again, we will put it here in injection molding. Why? To get the color shapes. The color shape, this piece, which we run further experimentation, either for morphology or for viscosity run, to characterize our result if we are hitting our target or not. So basically, when we are running the extruder, we should do some setting. I did like a small theory, call it GT, general trends. What is general trends? I set the 3 parameters: the speed, RPM, and the feed rate. So basically, I fixed, for example, from many experimentation, I reached that the speed 750 is good, and the 25. So I fixed the feed rate and keep changing the temperature to 30, to 55, to 80, then get the result. Again, for example, I changed the RPM, put it, for example, 700, 750, 800, and fixed the feed rate and changing temperature, or fixing temperature and fixing feed rate and changing, etc. Then we will get optimization, a high number of reading, and each sample should be characterized to see which processing parameter more effective to get the better color. So basically, using the extruded and injection molding, this palette, it should be molded in order to get the 3 shapes. One of these shapes, it is the measurement 25 meter diameter. Why? Because the rheometer, when you get the sample, it should be with this dimension for rheology test. Then we will run for rheological test, dynamic strain sweep, dynamic frequency. All should be used to study the material rheological. So I did here some photos. I did it myself from my lab before. This is the Coborian extruder which I use it. This is the Kawauchi molding machine, the pellet which we get it from here. We mold it here to get the color shapes. The color shapes, how we know the color? There is one American instrument called X-Rite 7000 to know what is the value of the color. This is RSG2 rheometer. This is also scanning electron microscopy. This is digital microscope. This is micro CT scanner. This micro CT scanner, actually, it is in Canada. There are two instruments, one in the University of Toronto and the second one in the hospital of Toronto. So it is very modern. It can, get a 3D with color and use for counsel, for medical optimization. So in our work, actually, we will study, as I said, the rheological characterization, and we will analyze the processing data. We'll get it from the rheological test, and the final of the project, we will correlate all results of the processing parameter, blending, rheology, and we will concentrate to see at the crossover point. We will show it in the graph. What is the crossover point, which it is important to find that the highest dispersion to get the best color in this point. So for the rheology, first of all, we will run dynamic strain sweep. We as you see from the graph, at the 3 temperature, 230, 255, 280. So it is strain with the viscosity. As you see, it is the first run till around 10. The shear is showing consistent. After that, showing shear thinning after 10 hertz. So basically 10 hertz, you can see the onset here, that at 280 showing lower viscosity compared with 250 or 230. So the onset shear thinning occurs at higher strain. So when you're getting higher strain, you will get more lower viscosity. Same here. I did another characterization which called validity of Cox-Mears. Cox-Mears, it means I run the experimentation for dynamic strain to see the shear effect and the complex viscosity shear rate. So both of them, it's showing they are consigned. So the shear viscosity is agreement with the complex viscosity. So they are almost consigned here, and when increasing the shear, then they start getting lower viscosity. So basically, I did this experimentation here showing at 255, but I did it also at the 3 temperature, showing the same result for validity. Here, this is the important one, the rheological behavior. So as you see here, I did it, the rheological test for 230, 255, 280, right? So basically, as you see, at any one of them, when you are increasing the frequency, you can see the viscosity and shear thinning start increase while increase it. Then also the tan delta start decreasing. Here, the loss modulus and storage modulus also increase. The cross here in this point, which we call it the crossover point, which I give it the value of it like 26 hertz to 10 power 5. At 255, we get almost the same result. We get the crossover point, but at 280 here, is not showing the crossover point. So basically, when G prime equal G double prime, this is called the crossover point. So which it is showing here before it is a Newtonian region, and after that, not a Newtonian, means it is correlated with the shear rate. And G dash double dash over dash crossover point at the 3 point, they didn't occur as you see here at 280. This is the result which I get it from the graph. And the crossover point, it's showing non-Newtonian after the crossover point. So basically, the shear thinning is observed by increasing the frequency, right? And the pigment dispersion is showing is efficient here. How we know it is efficient? because we run and we got the sample at 255. We find it 255 is the best one. And here at 255, you know, the crossover point, it is like entanglement or formation, like a gel material, after which it is G prime equal G prime. So it means the G prime is the storage modulus, which is showing like solid material, equal at that moment the loss modulus, which it is like viscous material. So also here from this rheological test, we run at the 3 temperature. As you see, when increasing the frequency, right, we showing that for 280 lower viscosity and more shear thinning. It's showing for 280, all showing shear thinning, but the maximum one at when we are increasing the frequency and temperature. Also, we run here to see tan delta. Also, it's showing a steady decrease, look, steady decrease in tan delta values with increasing the frequency. Also, this is the general trend which I run it to characterize these, to correlate the result of the viscosity with the processing effect of temperature on as a processing parameter. Look, the same sample which I said, you know, 2.1 inch, I get the sample, right, and I run it under under viscosity test and under processing parameter test with the color. So the same 3 shapes, I get it at 3 temperature, 255, 280, and 230. I check the color for this value. I find when we increasing the temperature, right, when we are reaching to about 255 here, right, until 280, which is showing shear thinning here, right, here, and 255, it's showing the best color. How we know the color here it is good? Because we know when DE value, the color, this, when it is less 1 or when it is approached to 0, it will showing the best color. So basically at 255, look, it is the value here, it is less 0.4, so it is very low comparing with the requirement. So also I run another characterization test for master curve. What is master curve? It is basically used for like a testing for broad range of angular frequency, what to predict like the material behavior over a broad time. So basically it gives us also, we simulate the viscosity model for all these 3 temperature, and for even the master curve, we get this formula viscosity, which call it Cario model with fitting parameters C1, C2, C3. Also here, this is the value for the experimental simulation of the Cario model to 3255. This is the value of parameters I said, which it has helped us, you know, to get the proper viscosity. We can working in these parameter, and this is also the model for the master curve with the parameter, and this is the formula for the viscosity model. So now we are approaching to the end, which the more important slides. Here it is this diagram, and this is showing almost the result of all our work. What is this? This is the graph. This is the pigment size distribution with the effect of temperature. You remember we did here effect of a 3 temperature, right? So we get here the value of 255 or 280 is the best color, right? Here we run also the same sample. We run something called pigment size distribution. We get the graph. When we take the graph by digital microscope, we can calculate by histogram, you know, the number of particles for each photo. For example, we run at 280 here, we get the number of particles 55%, right? When we run at 230 here, we get the number of particle 49. So basically we are concluded in when increasing the temperature, we get the number of particle is high. And what is in x-axis we get is the 0.8 micron of the size of the pigment size. So this is, we correlate this one with the general trend one, the previous one, which I showed recently. Now this graph, it's showing all the graph. I did it at 3 temperature, 230, 255, 280. For example, here we run it here at different frequency. You see here, for example, the green one is 280 high frequency, the red is the 255, this is the 230. When we increase, look here, for example, at 280, the frequency at 280, look here, tan delta, we see it is high at 280. Here, medium is lower. Here, the average, the diameter or the size of the pigment at 280, we get lowest. So it means when we increase the frequency and temperature, the pigment size, we get lower. Why we get lower? If we get lower size of pigment, we will get better color. It means good blending and good optimizing of the result. Here, the number of particles. Look, when getting high frequency or high temperature, we get here the number of particle increase. As we see here, you see, when we get to 80 temperature, we get the number of particle 55. This graph, we can put it here in a different area. So basically, number of particle increase with increasing the temperature. Same here. Finally, this is the more important to get the color value. Color value, when we increasing, for example, the temperature to 80, is the green one, we get lower DE, lower DE, as we see it in this graph before, which show it the general trend, this one. So at 280 or 255, you see the color value is low. So this is the color value when we increase the temperature is low, comparing with 230, which is showing a higher value of the color. So basically, a proportional relation for example, for frequency, delta, number of particles, the color, average diameter, for all they are showing significant approach, indicated that the dispersion model is efficient at where here at 255 here or 280 when we increasing the temperature. Finally, the final slide here. So I don't know if I am approaching to the time or not. So I try to go fast because I think I finished in the 20 minutes or more. So basically here we get the morphology. I use actually three type of digital microscope or the scanning. The first one is digital scanning electron microscope. This slide here I use digital microscope, and here CT scanner to see how's the agglomeration of the material showing. So basically, when we are increasing the temperature here, as you see, here a lot of agglomeration. You see, when we increasing, the agglomeration is showing much less when we are increasing the temperature. Comparing here with the digital optical microscope at 230, which it is low temperature, we have seen here higher agglomeration, and the CT scanner here it's showing to you the one here, the agglomeration, how see it is big, and at the central level, which it is 255, which it is the optimum point, it's showing less. So basically at higher temperature, less agglomerates are evident at 280 than at 230. So, and here from this slide, we can see the number of particles, same in the graph, and we see the particle size of pigment, which it is actually a higher temperature has good pigment dispersion with less amount of agglomerate observed, and the average of the particle size or the pigment, it is almost about 0.8 micron. So finally, the conclusion, as we have seen that the scanning morphology examined by scanning electron microscopy, digital optical microscope, and UT scanner, all showing at higher temperature has a good pigment dispersion with lesser agglomerates are at 255 and 280 than 230, and lower color difference observed. And finally, the dispersion mode efficient at a crossover point at almost 255 and 280. So therefore, maybe this is regarded rheological threshold composition. Finally, I am sincerely appreciate your attendance this morning. And actually, if anyone has any question, I will do my best to answer. Thank you. And I would also like in the end to thank all the organizing committee who made this event a success. It started with the Professor Hamouti and Professor Tozani and all the committee and the moderator as well and the attendance. Thank you so much.
Thank you, Professor JAMAL ALSADI, for these nice presentations and applications of your rheological system to identify pigment in the polymer. And now we open the session for questions, if there is any.
Yeah, good morning. I have one question. May I ask?
Yes, go ahead, please.
Yeah, so thank you so much. And good morning, Sabah al-Noor. Yeah, did you, I see that you optimized the temperature, no? And then did you, let's say, optimize the temperature, let's say like 280, whatever, did you look at different polymers with this condition?
Okay. Good questions. Your question, it can give indication to apply my experimentation to different polymers. Basically, in my research, I concentrate for the polycarbonate. Polycarbonate, I choose it because it is so expensive material, use it in aircraft, plane, cars, everywhere. But basically, so far, I apply it, to be honest with you, only for polycarbonate, but I am ready to apply it as well for any different material if it is requested.
Yes. So it's interesting also because, it is a very important field, of course, in many applications. One of them, for example, LED. LED, when we use, of course, like polymer, photoconductor polymer, cyclic polyvinyl carbazole, for example, and others, of course, there are many, yeah. So maybe it's very interesting to see if, using specific dye, which is very interesting in LED, for example, and use this technology, to see how this dye dispersed within polyvinyl carbazole or another one, no? Of course, yeah.
Yeah, you are absolutely, you are right, absolutely.
Yeah, maybe we will see what. So later we will talk, of course, during the next days, next month. Maybe you can do something together. Yeah, from here. Here in Spain, what I'm doing also with the dyes, some specific dyes and particles, of course, also like mauve particles, for example, or like others, and try to make a new LED. So another question which I have, if the chairman allows me.
Yes, please.
Yeah. So what is is there? I see the temperature effect is clear and crossover and so on. What about, let's say, the light intensity effect? So you have the sample there, and you shine light. You can shine light, let's say, at different power or different fluences, depending if the light is pulsed with a continuous regime and so on. Do you have something about that? Do you know something about that?
Sure. First of all, we have some scientific expression called meta-racism. This is, if, for example, two persons look to the same color, they will see it not in the, for example, if you go yourself with somebody to buy some clothes, look, maybe some people, they are looking different color, even it is same color. Why? It could be affect, the light. If you're using, for example, a fluorescent, it is different from normal lamp. This is one issue. Second issue, even the power of your eyes, the blueness, you can see it not 100% same different. But according to our experimentation, we have, the spectrophotometer, which I show it to you in the picture. and maybe I can show it to you again. This one, the spectrophotometer. This one is designed according to color space. There is two. It can measure it in different ranges, which call it D65, and you can use different range or extension. And there is more technology is using, and now they are using more digital to examine the color directly. So basically, DE it is here measured with according. If you go to the specification of a spectrophotometer, it's showing to you a fix what is the use of the light or the power of this light according to spectrophotometer. Some people they can actually characterize the color according to their normal eyes. It could be possible also, but according to calculation and for big experimentation, you know, for example, now some company they are requesting the cover of your mobile, right? You know, the color, some people they are believe it is so easy, like 3-4 color. No, the color is million of color. You know, for example, you have red color, you have many codes, yellow, blue. So if you mixing, for example, blue with yellow, you will get different colors. So it is, if you are going to paint your car, for example, so he mixing to you some color, you will get different color. So this is complicated issue, you know, in order to characterize the right color. So any mixing with different codes, you will get millions of color. So because of that, they are manufacturing the spectrophotometer in order to give very accurate reading, not depends for the meteorism or for your eyes.
Just a curiosity, yeah. You know,
Yes.
the model which is about defining the colors and what we're talking about now, what is the difference between the known model also in what you call CIA, this Commission d'International Electricité in French, yeah? So what is the difference between them?
Basically, you know, there are different companies, you know, the science is like it is business, you know, marketing. Some company using, yeah, exactly. So they are using different range of color or different, you know, lightness or strong light, you know, the range, something like that. But basically, they are all concentrating for the same idea. Yes, sir.
Yeah. Thank you so much. So thank you so much.
You're welcome.
Thank you, Professor Duhal. There is any other question, please? Just a reminder that the virtual ICMES 2020 closing session today at 12 o'clock local time Morocco, which will celebrate the award of the best student oral presentations. Please, you are welcome to be with us.
Inshallah.
If there is any question, I will declare that the session is closed. And also, I remind you about another conference with at 10:30 with Ever at 10:30. He will talk about perovskite and solar cell. Please, you are kindly invited to assist. Professor Hamouti.
Yes, thank you, Professor ALSADI, for this nice. Thanks so much for sharing these experiences about colors. Thank you so much. Thank you so much, Professor Touzani, for moderating this conference, and hope to meet you after 30 minutes in campus of the university.
Thank you, sir. Thank you, Professor Hamouti and Dr. Touzani, and Professor Touzani as well, and the moderator. And I am really sincerely appreciate your cooperation to make this event so successful. So thank you so much. Assalamu alaikum.
Thank you, everybody, and see you later at 10:30. Goodbye.
شكرا جزيلا.
يا هلا. السلام عليكم.